All right, kids, how's it going out there? It's time for another amazingly exciting adventure, if you will, into the wonderful world of thermodynamics. Yes, so again, I'm going to try to tell you, try to contain yourselves. I know you're excited. All right, anyway, so up until this point, we've been talking about thermodynamics, which is heat energy, okay? And that heat energy has all been about physicality, okay? We haven't talked about chemical changes as far as heat goes, okay? For example, you know, you take a hot piece of metal and you drop it into some water. The water temperature is going to go up. The metal temperature is going to go down, but it's still metal and water. There's been no chemical process. Even if you drop ice into water, right? You take some ice out of the freezer, you drop it into your coffee or your tea, maybe it's a little hot and you can't take it. It's too hot, I need some ice. So you put some ice in, and obviously the ice melts, becomes cold water, and the temperature of the tea or coffee or hot chocolate or whatever you're using will come down to a more drinkable temperature, if you will. Okay, but all of those processes were physical, okay? Even if you were to take some water and warm it up on the stove, even not to the boiling point, that's all still in the physical realm, all right? There's been no chemical change, okay? Here, though, enthalpy is going to be a little bit more about the change via some kind of chemical reaction, okay? So I chose this, which is in the notes too, but I chose this combustion reaction, all right? I don't want to go over a little bit about what this means. It is in your notes, but I didn't really go into a lot of it other than to tell you that the enthalpy is basically the heat that is gained or lost in some kind of a process. And that process is typically going to be a reaction. Okay. The symbol for, or the sign, whatever the heck this is called, delta H. That's going to be our enthalpy change. Remember, delta T is the temperature change, T2 minus T1. Okay. So what this means is as the reaction occurs, you undergo some kind of enthalpy change. And I picked the combustion of propane gas, like in a gas grill. I just fired up my grill last week for the first time. I got a nice Phillies grill cover. It's looking really nice. But this is what happens when you hit the ignite button. You know, you go and you undo the thing, and then you hit the ignite button. Now, if you're using charcoal, this is totally, irrelevant to you, right? But this is basically what happens, okay? And what this means is when this equation is balanced, it's not balanced yet, but you can do that. When it's balanced, this is the amount of heat energy that will be produced by the balanced equation. Now, I want to talk a little bit about the negative versus the positive. I kind of skipped over the first page of the notes. I don't want you to skip over it. I skipped over it, but here's what it means. When this delta H value is negative, okay, that means the reaction happening, the enthalpy value being negative, means that heat is going to be given off by the process, all right? Which, think about it, you turn on the gas grill, and if you put your hands there, you can feel the heat coming off. That's what this negative sign means. It gives off energy. But what you can do with enthalpy is you can take the products, bring them over to the reactant side. Take the reactants, bring them over to the product side. That's called reversing the reaction. Well, if that's the case, you can reverse the reaction, but instead of it being negative 2,220, this is kilojoules, by the way, just because the joule unit's too small, the kilojoule's a little bit easier to use in this sense. If you bring the products over to the reactant side, and you bring the reactants over the product side, the delta H value, the enthalpy, would be positive 2,220. Meaning you would have to put energy in to the system in order to get that to occur, okay? The examples on the first page of the notes, I think it was hydrogen plus oxygen yielding water, H2 plus O2 yielding H2O. But if you flipped it and it was the H2O breaking down into H2 plus O2, which you would need to do via electrolysis, you would have to put energy in order to split in order to split the water into the two components of hydrogen and oxygen. And it can be done, but it requires energy. That delta H value would be positive, okay? All right, but when you burn something, it happens spontaneously and it gives off energy, all right? So what this means is, this is the amount of energy given off when the equation is balanced, okay? But right now, the equation isn't balanced. So I would give you about 2.5 seconds to balance this if it was class time. And what you would do is you'd say, all right, well, we got 3 C's and we got 8 H's, right? Which, so you got 6 O's here and 4 more makes 10. So the coefficient there is a 5, right? Which means this coefficient, even though I didn't write it in, is a 1. Now, I typically don't write the 1s in. I don't expect you to either. But what this equation means, when you take 1 mole of propane and you burn it in 5 moles of oxygen, oxygen's O2, not O, right? It's one of the diatomic molecules. You produce 3 moles of CO2 and 4 moles of water, usually in the form of vapor, because this is a very exothermic reaction. Okay, when that happens, 1 mole of this and 5 moles of this and 3 moles of this and 4 moles of this, the enthalpy of the reaction as written, 2,220 kilojoules of energy are given off, okay, from the system to the surroundings. All right, so let's talk a little bit about what the first problem says in your notes, the first sample, okay? It says, what is the heat evolved if 454 grams of propane are burned to give this reaction? Now, 454 grams, I think I got this problem out of a book a while ago. They chose 454 grams for a reason, and that's because 454 grams is equal to 1 pound, for the most part, right? Well, unless we were on the moon, then it wouldn't be, but since we're doing the reactions here on Earth, that's all that matters, right? Okay, so what I know is 1 mole of C3H8 will be negative, or with 2,220 kilojoules of energy would be released from the system to the surroundings. Okay, well, that's if we had 1 mole of C3H8. But I have, it said, 454 grams of C3H8. Now, most of us, if you've been paying attention even a little bit this year, you should know that grams can go to moles by Uncle Starach's Holy Grail. And you just need to use your PT Cruiser, all right? Okay, so you go from grams to moles by using the periodic table. Okay, so what we're going to do is we're going to say, well, 454 grams of propane and 1 mole of C3H8, I believe, is 44.094 grams. If it's not right, you can correct me later. I'm not going to do another whole video, but I'm pretty sure that propane is 44.094 grams. Okay, so we got 454 divided by 44.094, and we end up with 10.296. All right, so why don't we call it 10.3 moles? All right, so we got 10.3 moles of propane, which is C3H8. Now, honestly, kids, I didn't really teach you anything that you didn't know how to do. You pretty much knew how to balance an equation. I gave you a classwork with like 175 on them, plus the big daddies, right? Okay, grams to moles. 1 simple conversion factor using the periodic table. Okay, now wait for how hard this is. I want you to wait for it. Okay, if 1 mole of propane will release 2,220 kilojoules of energy into the atmosphere, well, then 10.3 moles of propane, which is C3H8. Come to think of it, I don't even really need to tell you that it was C3H8 because we know how to count to 10 in organic chemistry, right? Meth, eth, prop, but, pent, hex, hept, oct, non, dec. And then we have anes and enes and ines. And anes are saturated, which means the C is N and the H is 2N plus 2. But you already knew that, didn't you? All right. So that's, as I went off on a little tangent there, forgive me. Okay, so this is basically what we have, right? So you got 10.3 moles of C3H8. Well, 2,220 kilojoules of energy are released by 1 mole, all right? So really, what you got is 10.3 moles times 2,220 negative, all right? So the heat energy released by 10.3 moles, and I'll round it to 3 sig figs just to keep it going. Let's say 22,850. All right, so negative 22,900 kilojoules, and I box that bad boy off just like that. Okay, and that's how we figure out the enthalpy of a reaction. Now, here's what I would like you to do. On my computer here, it says, what is the quantity of heat evolved by 1.50 kilograms of octane? Okay, 1.50 kilograms of octane. And then I gave you the formula. And the formula is C8H18 for octane. So while you're waiting for me to write it up here, why don't you first balance the equation for me for octane while I rewrite it here for you, okay? All right, so we got our octane is C8H18. Hopefully most of you know it's a combustion reaction, so I shouldn't even need to tell you that it's CO2 and H2O, okay? Octane is the basically what gasoline is. It's very, very, very exothermic. The delta H value is negative 11,018 kilojoules. Okay, so here's what we're looking at so far. All right, so there's the octane, and it says 1.50 kilograms. All right, that means we have 1,500 grams C8H18. Okay, but okay, while you were balancing this, and hopefully you did, it's important to know that the enthalpy value that's given here, obviously you burn gasoline, it releases energy. That's what makes your car go. That number is only when the equation's balanced. All right, and what you would have found is if you went 8 and 9 here, you'd see you'd end up with an odd number of O's. So to balance this, we got to go 2, 25, 16, and 18, okay? Right, you got 32 and 18 is 50, so you're 25 times 2. Okay, so now what this means is the combustion of the balance equation is 2 moles of octane are burned in 25 moles of O2, releasing 16 moles of CO2 and 18 moles of H2O to the atmosphere once the combustion of the reaction is finished. Okay, so what this means is negative 11,018 kilojoules are for 2 moles. Okay, so let's figure out how many moles we got. All right, well, we got C8H18. This is another one I'm going to go with, hopefully remembering off the top of my head. All right, so we got 1,500 grams of C8H18, and 1 mole of that, according to the periodic table, 114.112 is ringing a bell, but you know what? I'm going to check it anyway. All right, so we got 1.008. Sorry, I don't have my scientific calculator. 1.008 times 18, okay, plus, what's that, 96.08. 114.224. I was close. I think I said 114. Maybe I did say 224. Go back and check the tape and we'll see. All right, so we got 114.224 grams of octane like this. And this should be able to give us our number of moles. All right, well, 1,500 grams divided by 114.224 grams is going to give us 13.13 moles. Huh, that was rather unlucky. 13.13 moles of C8H18. Okay. All right, now from here, it's pretty much just like the problem we just did. There's one little tiny difference, and that is that this is the enthalpy for 2 moles, not the enthalpy for 1 mole. So when I set up to figure out the final enthalpy value for the amount of 1,500 grams, we're going to set it up like 13.13 moles of octane, which if you remember when we were doing the organic stuff, I said octane's actually 2,2,4-trimethylpentane. It's not a straight alkane chain, although it still is saturated. Okay, so this is how I'm going to set it up. I have 13.13 moles, but you got to remember it's negative 11,018 kilojoules for 2 moles because you're balancing the equation with a 2 there. All right, so your moles will cancel. The other thing is you could have said that it was whatever half of 11, what's a half of 11 down? 5,509 maybe, something like that. 5509 kilojoules per 1 mole. You could have done that. It would be the same, right? Okay. So you got to do 13.13 times 11,018 divided by 2, and I get this many kilojoules, 72,333. Let's call it negative 72,300 kilojoules. Now you might be like, well, how much is that, Uncle Starach? And the answer is, it would be about the equivalent of you burning 17,300 calories on a treadmill. Okay? That's how much heat energy would be given off by 1,500 grams of octane. Okay? All right, kids, I hope you enjoyed this lesson on enthalpy. And check out the note packet. And I will see you again soon. Uncle Starach is out.